Hey guys, hope everybody's doing all right. What we're going to look at today is the first lesson in our new unit, and that lesson is on ionic and covalent compounds and the main differences between those in terms of properties, and just a brief discussion about the solubility rule. So, starting our new unit here, elements bond chemically to make compounds. Okay, so we talked a little bit about this in some previous units. We just kind of touched on it very minimally, but we're going to go into obviously more detail right now and look at the properties that these compounds will have and the specific types of bonds that occur and why different elements make certain bonds with other elements. The type of bond holding the compound together will determine what kind of properties it will have. So the two main types of bonding, we probably saw it on the previous slide. We have ionic and covalent bonding. There's also metallic bonding that I get into in AP Chem a little bit, but we're going to focus on ionic versus covalent today. You probably recognize those terms because back in our nomenclature unit, we have different rules for naming those compounds, right? We have rules for naming ionic compounds, and we have rules for naming the covalent type. What I would normally do, or what you guys would normally do right now, is a properties of compounds lab. So we would take a look at some different ionic and covalent substances, and then we would compare properties of the two. So we would look at melting point, we would look at solubility, electrical conductivity. So we won't be able to do that in the virtual lesson here, but we'll still take a look at what those properties actually are. So the first one we're going to look at is ionic compounds. What I always ask students to do when I introduce this is to think of a very, very common, everyday ionic compound. And hopefully, if I ask you that question, you're thinking about regular table salt, right? So that's the most common example of an ionic compound. I talk about it in class all the time when we talk about ionic compounds. What I tell students to do is know that salt is ionic, okay? And then just think of all the properties that salt has. If you could think of that, if you can do that, then you don't really need to worry about memorizing basically any of this stuff. So salt will have a high melting point. So it'll be what at room temperature? Well, just think about it. What state of matter is salt at room temperature? Well, it's a solid. Most ionic compounds, I can't really think of any that don't follow this, are going to be solid at room temperature. That has to do with the type of attraction the ions have to each other, and some of that again is more of an AP level analysis of this. But what you guys need to know for now is that they have high melting points, and they are solids at room temperature. They're also very brittle. You can see a picture of the nanoscopic view here of table salt. And if you were to whack this with a hammer, this section here, like see you whacked it right here, this negative ion would get bumped down, and it would be next to this negative ion. Well, like charges repel, right? So those two negatives would line up, those two positives would line up, and all that repulsion would push it apart. So I think that's pretty interesting for why that's true. Okay, next one. They're blank in water. Okay, well, ask yourself this. Does table salt dissolve in water? Well, obviously the answer is yes. So ionic compounds are soluble in water. And then we did this as part of the acid-base lab as a little part of our analysis there and looking at the properties of acids and bases. We did an electrical conductivity test. So you may remember salt water was one of those that I tested. So electricity, what will it do with electricity as a solution in water? Will it conduct or won't it? If you remember, salt water was a very, very, very good conductor of electricity. Even though salt water was a neutral substance, it still conducted electricity very well. I have a little mini demo that you'll watch in a few minutes, or before the next slide on that. And this goes back to our nomenclature unit. It consists of a metal bonded to a nonmetal. So obviously sodium chloride, table salt, Na. Sodium is your metal, and chloride is your nonmetallic component there. All right. So we'll look at the mini simulation here of why salt water and salt specifically conducts electricity, and then we'll move on to covalent compounds. Okay guys, we're going to look at a simulation here where we're going to test the conductivity of salt and sugar. So here's my water. I put my conductivity meter in there. I did something similar to this in the acid-base lab, if anybody remembers that, where I had all the different acids and bases or neutral solutions, and I had a really old-looking ring stand with a light bulb on it with some electrodes, some copper electrodes, and I put the electrodes into the solutions, and we recorded if they conducted electricity or not. So for this one, we have our regular water here, and we have no conductivity of electricity. I add a little bit of salt to it, like that, and you can see I'm now conducting electricity. Okay, you can clearly see that in the simulation here. If I add more salt to it, you can see that things escalate quickly here, right? So we have more conductivity of electricity. Our light bulb is brighter. So why is that? Let's look at the micro tab. Let's look at what happens at the microscopic level. So here's my sodium chloride, my table salt, NaCl. Over here on the right, I have my pink and green colors. Pink is sodium ion, green is chloride ion. And if I shake some of that into my water, clumps of it go in, and now look, we have the sodium ions in pink and the chloride ions in green moving away from each other. So we call that dissociation. The ions have dissociated from one another, and now they're floating around in here. Well, why does that cause that solution now to conduct electricity? Well, you have to look. For electricity to flow, for something to conduct electricity, you need some charges in there, right? For those electrons to move. So we have our positive ions in sodium and our negative ions now in chloride. So we now have those positives and negatives in the solution here, allowing electricity to flow. Well, why did we have more electricity and a brighter light with the more salt we put in? Well, if I just add some more of this, if I can, okay, I'm out already. I now have more ions in here, right? More ions in solution means a greater conductivity, right? So if I went back here, added more salt and more salt, you can see that I conduct electricity a little bit better. Okay, again, I'm out apparently, but that's what would happen in this one. When you think of covalent compounds, you want to think of what? What are some common molecular or covalently bonded, really means the same thing, compounds in everyday life? Well, two I could think of are water and carbon dioxide. Both of those are obviously very, very common, and both of those are molecular or covalent. So when you answer these questions here, you want to think about water and carbon dioxide specifically. So again, don't memorize a bunch of this stuff. Just think about, okay, I know water, I know CO2, I know carbon dioxide, I know they're covalent. So let me think of what properties water and carbon dioxide have. And then you know all this stuff without really any memorization whatsoever. So obviously water and carbon dioxide have very low melting points. Now not all covalent compounds do, but the vast majority do have low melting points. Many are liquid or gas at room temperature. Some are solids. Okay, there are always exceptions here. Like sugar. Sugar is a covalent compound, and of course sugar is a solid at room temperature. But a lot of them are liquids or gases, and the two I'm asking you to think about, water and carbon dioxide, follow that trend. Okay, do they conduct electricity as a solution in water? Well, this is the opposite of an ionic compound basically in terms of this property, so they don't conduct electricity. Covalent compounds are non-conductors. They're sometimes soluble in water. Here's where it gets a little bit more confusing, and we get into this more a little bit later when we classify these compounds. But if you remember from bio, and I know you learned this in biology, what type of substance is water? Is it polar or nonpolar? You probably remember that water is a polar substance. So we have two different categories of covalent compounds. We have polar covalent compounds and we have nonpolar covalent compounds. The polar covalent compounds will dissolve in water. The nonpolar covalent compounds will not. Okay? We'll take a look at in the next lesson how do we determine if a compound is polar or nonpolar. It all has to do with the elements involved and their electrons and how bad they want more electrons. Okay? Covalent compounds, you may remember from the nomenclature unit, consist of all nonmetals. So water is hydrogen and oxygen, two nonmetals. Carbon dioxide, carbon and oxygen, two nonmetals. sugar, carbon, hydrogen, oxygen, all nonmetals. The list goes on here. So covalent compounds are going to be nonmetals only, whereas ionic, you start with a metal and end with a nonmetal. So we're going to take a look at the conductivity simulation here for covalent compounds, then we'll move on to the solubility rule. So if I try sugar, I pour sugar in. Look at that. No conductivity here. No electricity being conducted. So why is that? Well, let's look at the micro tab and figure it out. So let me change to sucrose, which is just sugar. Look over here. Sucrose is in the form of C12H22O11. That's a molecule. Okay? So a molecule of sucrose looks like this. All right? Let's add some to our regular water. A couple clumps. Now, the sucrose molecules do move away from one another, right? But look, we had sucrose molecules when we added them, and now we still have sucrose molecules, right? So if I could pause this somehow, I actually can't. Okay, if I pause this and I look at one of these, this is one molecule of C12H22O11. Here's another one, here's another one, here's another one. Molecules are neutral overall, right? So I don't have any charge here on that sucrose molecule. That sucrose molecule is neutral. So I added sugar to this, and it's not changing like the charge. There's no ions in here, right? It's not like this is dissociating and I'm creating ions with carbon or hydrogen or oxygen. It's not occurring like it was with my NaCl and my table salt. So that's why when I go back here and I add my sugar to this, those sugar molecules have dissolved. They're in here, but they're still together as individual neutral molecules. So there's no electricity being conducted here at all. This will work with, let me remove this. This will work with any solute, okay? So calcium chloride, I do this a little bit in AP Chem. I actually use the same simulation. Calcium chloride, if I add that to my water, calcium chloride is ionic, right? So when I put that in, if you know what the formula is for calcium chloride, if I add this, the ions are going to dissociate. All ionic compounds dissociate, okay? So now look, because my formula is CaCl2, I have one calcium ion for every 2 chloride ions. So if I could go back to my macro tab, and if I added calcium chloride salt to this, I actually would have a greater conductivity and a brighter light than if I had the NaCl, the regular table salt. NaCl, if you look at the formula, dissociates into 2 charged ions, Na plus, Cl minus. Calcium chloride dissociates into 3 ions, 1 calcium and 2 chlorides because of the formula. So you have more ions floating around that are dissociated with calcium chloride compared to with sodium chloride. Okay, so that gives you a little bit of a microscopic or nanoscopic view into the difference between ionic and covalent compounds or molecules, and why some conduct electricity, which are the ionic compounds, and why covalent molecules and covalent compounds, they do not conduct electricity. Okay, so why do elements want to bond to one another? Why do they want to bond at all? The short answer to this is atoms are always searching for ways to be more stable. Now the question is, what does that mean, right? What would make an atom stable? Well, if you go back to some of the previous content from last unit, you may remember that atoms are always trying to bond in order to achieve an octet. An octet is how many valence electrons? Right, it's 8. So 8 valence electrons, that's what every atom is striving to get here. Okay? There are multiple ways atoms could get an octet of electrons. They could steal electrons from other atoms, or they could share electrons with other atoms. And we're going to look at those in the next lesson, actually, and kind of analyze those a little bit more. So, to wrap this up here, I talk very briefly about solubility. And why do certain things dissolve in certain things? Why do some things dissolve in water and some things don't dissolve in water? The solubility rule is really 3 words. like dissolves like. You're going to say, what on earth? Like, what on earth are you talking about? It's easy. You could write this down if you want to, since you have time here, but you don't really need to if you kind of understand what's going on. You need a solute and a solvent, right, for solutions to be made, for dissolving to occur. The solute is like your Kool-Aid mix, and your solvent is water, okay? Solute is what is being dissolved, and the solvent is doing the dissolving. So when the solute and solvent match up in terms of polarity, then they're going to be miscible with each other, and they're in a mix, okay? So polar compounds dissolve in polar solvents. Therefore, nonpolars dissolve in nonpolars. And this looks a little weird right now. It won't look as weird next lesson. Ionic compounds dissolve in polar. What we want to think about for ionic, you want to think about something that's ionic as being super, super, super polar. Okay, so something that's ionic is like ultra polar. So it's going to dissolve in something that's polar, like water. So the image on the screen here is an example of a density column. You may have made one of these during a home experiment, or if you remember my chemistry display that I had a 4-layer density column with red and clear liquids. So the reason why this occurs, one reason is because of density, right? The honey is the most dense substance here, and the vegetable oil is the least dense. But it also has to do with polarity. You have to make sure that these layers alternate polarities. So honey has one polarity. Corn syrup has the opposite polarity. So you know vegetable oil and water don't mix. And water is polar. So what does the vegetable oil have to be then if they don't mix? Well, the vegetable oil has to be nonpolar. So we have a nonpolar layer, polar, for water. That means dish soap has to be nonpolar, and corn syrup has to be polar, honey nonpolar. You know what I mean? Like you get that alternating polarity there, which is why they're not going to combine. And they stack on one another, because of the different densities that they have. So there's a little clip here I'll show you towards the end of this, where you will look at like a mini version of this density column. Okay, just like a disclaimer here. The solubility rule of like dissolves like will work for now in terms of explaining why something dissolves and something doesn't. But if you signed up for AP Chem and you're taking my class next year or when you're a senior, this explanation is no longer valid then. Okay, we have to up our game when we get to AP Chem, and we have to talk about intermolecular forces and attraction. Okay, it's really not that difficult, but we don't really get into much of that in honors because it's too much. But right now, this is okay for now. So enjoy it while you can. All right. We'll watch the clip in a second here once the last few slides are wrapped up. So everyday solubility rule in action. I think this is really interesting. Dirty, oily hands, right? So this person's clearly working on something mechanical here. The grease and oil is nonpolar, and if you try to wash it off in just water, then it's not going to be that effective. You might be able to rub some of it off, but it's not really going to dissolve and go away. So what do you have to use? Well, of course, you have to use soap, right? So what does that tell you about the polarity of the soap? Well, nonpolar grease and oil and polar water don't mix. So you need to add something to that, right, to help get that grease and oil off of your hands. So an example could be your nonpolar grease and oil on your hands, and then you have some nonpolar solvent like this. So the nonpolar solvent helps dissolve the grease and oil, and the water could help just wash it away and rinse it off. Painting is the same thing here. So you might have an oil-based paint or a latex-based paint, and it doesn't really mix well with water, and the water doesn't clean your paintbrush off very well. So if you use a paint thinner is a nonpolar solvent. Okay, so that's going to help dissolve the paint, and then of course you rinse it out under water, and that just pushes it away. Dry cleaning is the same thing, or even your laundry. Okay, so you have dirt on your clothes. You add some detergent, it helps lift it off, and it's attracted to it, and then it maybe will float to the surface, right? And then the water will the washing machine will wash the rest of it away and drain that water out that has the dirt attached to it now. You know what I mean? So using a dry cleaner is really just a solubility rule in action again. So we're going to watch that clip real quick on the density column and the solubility rule, and then we'll wrap things up.
Nonpolar carbon tetrachloride is poured into a test tube. When the nonpolar colored solid is added, the solid dissolves in the carbon tetrachloride. When polar water is added to the test tube, it forms a layer on top of the carbon tetrachloride, since water is immiscible with and less dense than carbon tetrachloride. When nonpolar hexane is added to the test tube, it forms a layer on top of the water, since hexane is immiscible with and less dense than water. When the test tube is vigorously shaken, the two nonpolar liquids form a single layer at the bottom of the test tube, and the polar water layer sits above this layer.
Okay, last thing you want to do is go to page 3 in your packet and take a look at what's going on there. It's just an overview of an experiment you would have performed, and it gives you a bunch of sample data. A through D are just the steps you performed in the hypothetical lab. So what you want to do is fill out the data table and answer the 2 questions that are below it. It's really easy. So use the notes from the lecture today. All right, go back and look at what the properties were of ionic and covalent compounds. Compare that to what you guys have on that lab, and then try to answer the questions as best you can. And you might end up classifying certain things as ionic and covalent. Use your notes, you'll be just fine. You're going to input your answers into Edpuzzle, and that will be how you get your assignment grade for today. All right, hope this made sense, and see you guys later.